This is Space Nuts, episode 248 with Andrew Dunkley and Fred Watson. Fred, the other day somebody pointed out that for 2 weeks in a row we both wore pink shirts.
Yeah, we did. I noticed that too.
Did we do it on purpose? No, it was a complete accident. But I noticed today we're both wearing navy blue.
Yep, we are. Yep.
So, and of course, if you follow us on YouTube, you would be aware of that because you can watch us. I don't know why you'd want to see our faces. My wife doesn't want to see my face most days, but look, thank you to our YouTube followers, all 1.65 thousand of you. And, if you know anybody else who wants to follow us on YouTube, let them know because the numbers are ever growing. And we are just about, Fred, this is really exciting news. We're just about to crack 1 million downloads of the podcast.
Oh,
I knew that would come as a surprise to you, but at last count, we'd had 984,000 downloads. So probably by the end of the month or into May, we'll probably crack the million. So thank you to everyone who's been supporting the podcast and for listening for as long as you have. And many have been listening for a long time, some from the very beginning, some from about episode 70, and some started today. And if you are one of those, welcome. Hope you stick around and enjoy the podcast. Whatever platform you listen on, whether it's Apple Podcasts, Google Podcasts, Stitcher, there's a long list of them. Whatever your favourite platform is, you'll probably find us. And it's time to do some questions, Fred. So let's get straight into it. And we start with Richard in Brisbane. Hi, Fred and Andrew. Richard here from Brisbane. That's a coincidence because that's where I thought he was from. Love the show, love the content, love the dad jokes that Andrew seems to have an endless supply of. It's very sad and true. My questions are in regard to dwarf galaxies. Question 1, is there a common type of galactic centre for dwarf galaxies? I imagine they have some sort of central massive object, but is it a supermassive black hole or a solar mass black hole, a quasar, something else entirely, or nothing at all? And question 2, when a dwarf galaxy merges with another galaxy such as the Milky Way, what happens to the central massive object? I assume it's eventually absorbed by the supermassive black hole of the larger galaxy, and if that's so, does it separate from the dwarf galaxy's remnant stars, or do they get sucked in together? Question 2.5, add to this, what happens when two dwarf galaxies merge? Thanks for doing the job you do, guys. Please keep it up. Well, we were about to stop, but yeah, okay, we'll keep going just because of you, Richard.
Thanks, Richard.
Let's start with, is there a common type of galactic centre for dwarf galaxies?
Yeah, it's a really interesting question, and there probably is. And so I, did a bit of research on this question because I didn't really know the answer. And there is some work that was published last year, actually rather more than a year ago, which actually comes from Montana State University and other institutions. And the interesting aspect of this is it answers several of the questions in or the parts of Richard's question, because what this group found was massive black holes in 13 dwarf galaxies. Excuse me. Sorry, beg your pardon. They are now among the smallest galaxies known to host such massive black holes. So it's this is a new insight into our understanding of dwarf galaxies, because I think the consensus was until relatively recently that a dwarf galaxy would not have a supermassive black hole at its centre. And so that's, you when you look at pictures of dwarf galaxies, they're pretty ragbag looking things, they're not terribly well formed. They often don't have spiral arms, although some do. The two Magellanic Clouds that orbit our own galaxy, in particular the Large Magellanic Cloud, which you and I see in our skies, you particularly because you live in a fairly dark region of the state where you can see the Milky Way and the Magellanic Clouds. The Large Magellanic Cloud just has stubs of spiral arms. It's got a little bit of spiral structure and a kind of bar across the middle joining them up. And that's a characteristic of a much larger galaxy, but it's only a dwarf. And it's probably smaller than it started out as well, because it's having its certainly its gas is being removed by the gravity of the Milky Way. Something called the Magellanic Stream is streaming gas off the two Magellanic Clouds. You see it in radio telescopes. So this result that came out last year is really interesting, because it does highlight that these dwarf galaxies do have black holes at their centre, and some of them are what we call intermediate mass black holes. You know, the ones that seem to have gone walkabout, where we've got the stellar mass black holes, the supermassive black holes. These are intermediate. So to come down to just a few of the results, they spotted 13 massive black holes in dwarf galaxies located within 1 billion light years of our own galaxy. So they're relatively nearby, which they'd have to be, because they're fainter than the giant galaxies that we're normally looking at. All of the 13 galaxies are only 100th of the mass of our own Milky Way galaxy, or smaller. So they're 100 times smaller than the Milky Way.
Right.
But they've got black holes. That makes them among the smallest galaxies known to host massive black holes. And in fact, this work was announced last year, the beginning of 2020. The American Astronomical Society they have an annual meeting every January, right at the beginning of January. It was in Honolulu last year. Sadly, I couldn't make it, mainly because I was in far northern Scandinavia watching the aurora, but never mind. Anyway, that's where this result was published. But here's the crunch, Andrew. The black holes average about 400,000 times the mass of the Sun. So that is right in the middle of the intermediate black hole range. It's a bit on the big side. You're getting towards, not far off 1 million there. But so they really are intermediate mass black holes. But there's another punchline to this, which I think is quite extraordinary. These black holes were actively, eating material around them. But in half of the galaxies, the black holes weren't at the middle. They were kind of wandering around in the galaxy. So that's rather unexpected. You would expect that the massive black hole, or a supermassive black hole at the middle of a galaxy, is going to be plunked right in the middle, because it's where the gravitational center of that object is. But in these dwarf galaxies, that's not the case. And I suppose that suggests that there may be dwarf galaxies might be easily disturbed by bigger galaxies, so their structure might have been kind of pulled out of kilter.
That makes sense.
Yeah, there's a couple of quotes from the authors of this work. One is, "This work has taught us that we must broaden our searches for massive black holes in dwarf galaxies, but beyond their centres, to get a more complete understanding of the population and learn what mechanisms helped form the first massive black holes in the early universe." And there is another quote: "We hope that by studying them and their galaxies will give us insights into how similar black holes in the early universe formed and then grew through galactic mergers over billions of years, producing the supermassive black holes we see in larger galaxies today, with masses of many millions or billions of times that of the Sun."
So that probably answers, to a certain degree, the question about what happens when dwarf galaxies merge. The black holes would merge too.
Very probably, that's right. They've only found one black hole in each of these galaxies. If they'd found two, maybe that would be some evidence for an incomplete merger, if I could put it that way. Because I think normally, when galaxies merge, the black holes merge too. There's one interesting aspect of this, though, that there is still a school of thought. It's quite an old way of thinking, and is not agreed upon by everybody, but the globular clusters in our own galaxy. Globular clusters are really dense star clusters. The two brightest and biggest are in the southern hemisphere, again, which is one reason for putting telescopes down here. Omega Centauri and 47 Tucani are the two biggest of these objects in our galaxy. And some astronomers think that what you're seeing in a globular cluster is the stripped down core of a dwarf galaxy that's had all its outer stars pulled off by the gravitation of the Milky Way, but that the core of that galaxy is so gravitationally compact that it resists the what we call the tidal effects of the Milky Way and stays intact. And that actually makes a lot of sense, particularly because there have been one or two what you might call, I suppose you still call them intermediate black hole candidates discovered inside globular clusters. We think there are some globular clusters that have black holes in them, which highlights the possibility that maybe these are the the final remains of some galaxies that got too close to the Milky Way.
So basically, everything Richard's asked is possible to a certain degree.
It sounds like all the answers are yes, including question 2.5, which is what happens when two dwarf galaxies merge. Their black holes probably merge too.
Okay, what about the quasar theory that he came up with?
So quasars are a slightly different category, and they're kind of extinct now because they're a product of the early universe, where you had the supermassive black holes within galaxies really actively consuming the material around them. And they're so active that they're very powerful emitters of radio waves and visible light, in fact. And so the quasar regime has gone, but maybe, scientists wonder if all galaxies go through a quasar phase early in their lives.
Yeah,
that may not extend to dwarf galaxies, because you need a pretty big supermassive black hole to really kick off this process and get the kind of activity that you get with a quasar.
There you go, Richard. So the answers to your questions are yes, yes, perhaps, probably not, and maybe.
But not necessarily in that order.
No, not really. But thanks for your question, Richard, and hope things are going well in sunny Brisbane. I'm actually going up to Queensland later this year. We've got to go to a wedding. So hopefully all will be well come August, and I'll remember to take my hay fever medication. The last time we went up there for a wedding, we went in August, and I thought, that's only August, she'll be right, still winter. No,
no, not in Brisbane.
Got me good, because I was too far north. But thanks again, Richard. Now let's move on to a question or two from Tom in Toronto, Canada. Hello, Fred and Andrew. I'm a subscriber and admirer of your podcast since about episode 70, coincidentally. I have two questions for Professor Watson. I love this. Your Wikipedia page mentions few musical compositions you are a part of. How does the cosmos inspire your music, and does music inspire any thoughts or ideas you might have in your astronomical research? And then a really serious question. Could black holes be safely used in gravity assist? Greetings from snowy Toronto. Well, it was snowy New South Wales, Victoria and Tasmania this week. So as we in the north and southern hemispheres go through our seasonal changes, we're all sort of experiencing the same thing at the moment. But yes, your music, Fred. He's interested in your music.
Well, where to start? So I think it's fair to say, Andrew, I grew up in a musical family, and
so did
my dad was a swing, but he played in a swing band, and indeed my brother still does. They were both drummers, or they are. My brother still is a drummer. Although I have to
we
say,
won't hold that against them.
He doesn't. No, I know. He gets all the drum jokes. Yeah, he doesn't get many gigs these days for obvious reasons. So there was always music, but it wasn't just swing music. I mean, this is back in the 40s when I was a little one. Classical music was there as well, and that's what really got me hooked. I like pop music, but classical music has been something that has been a major part of my life throughout my whole life. And to be honest, Andrew, I'm really glad about that, because it often provides you with a way of getting away from the world. It's a really sort of solid thing to be able to listen to a piece of music that you know is going to be your happy place. Whether it's Beethoven or Sibelius or Brahms or whoever it is, it's all great stuff. So
Steppenwolf.
Steppenwolf, yeah, I can do that as well. You know, yeah, because I've got a fairly broad musical taste, and so that you know, in the 60s, I was heavily into the Beatles and the Stones and all the stuff that was going on then. But that's the other side of it. So my classical music is not entirely confined to listening, and I'll explain that in a second, but mostly because I don't play an orchestral instrument, for example. So I've never sat in an orchestra and played a violin or something. However, I did learn both piano and guitar, and in the folk era in the 60s and 70s I did a lot. I played in folk clubs all over England and Scotland, hung out with the likes of Jerry Rafferty and Billy Connolly and people like that who were up and coming musicians at the time, and you know, I still play occasionally, but not in any sense the way I was meaning to. I thought I was going to become a professional musician. I'm quite glad I didn't, because I wasn't actually, when I look back on it, I wasn't all that good. Never mind. The guy I played with was, though, he's still a professional in Scotland, Kenny Brill. We were two halves of a band called the Bradford and East Fife Ready Mix Concrete Company. Worked that one out. Anyway, you know, so the science comes into that, because for the last 50 years I've written daft science songs, which I perform at Signs in the Pub and things of that sort. Yeah. But the classical, in some ways, is more related to the astronomy, because I got very friendly with, because through his work, listening to his work on the radio, with an Australian composer by the name of Ross Edwards. Ross is one of Australia's foremost classical music composers. He actually composed the piece that was played on the sales of the Sydney Opera House on the 1st of January 2000 with an audience of 2.5 billion people. It's called Dawn Mantras. It's a beautiful piece of modern classical music. And not long after that, we hooked up the idea of making a musical journey through the night sky, which is his fourth symphony. And it's a choral work. It has two choirs to sing it. And I wrote the words, which are essentially the constellations that we recognise and stars that we recognise in the Western world, juxtaposed with the constellations that Aboriginal people recognise here in Australia. Now, they vary from place to place, so I just had to take selections. But it actually won an award, Andrew. The 2008 APRA Award for the Best Choral Work of the Year, because it came out on a CD. So
APRA being the Australian Performing Rights Association.
That's exactly right. The two things are very much intertwined in my brain. And really, I can't answer Tom's question, because I don't know how it is that these things inspire each other, but they definitely do. I do, when I'm writing, I often, like this kid's book, I know it sounds daft to say it in a kid's book, but I'm often subconsciously aware of the structure in a piece of music. You know, the exposition, the development, the recapitulation in a piece of what's called sonata form often goes into the way I write things. You set off with an idea and you bundle it around a bit, and then you come out with the same idea but in a different form at the end. Once again, I don't think that answers the question. Let's get on to the real question anyway.
Fascinating, though. Fascinating. Yes, he says, could black holes be safely used in gravity assist? I assume this is like space travel.
Yeah, it's an interesting thought, and what little I know about the mechanisms of gravity assist suggests that I don't think they could, because
too big.
It's more that they don't have that they don't have structure. So look, I'm kind of guessing here, just, you know, so these are ideas pulled out of the air, but gravity assist is weird, because if you think about it, you know, what's happening is you're flying a spacecraft close to a planet, it's feeling that planet's gravity to increase the speed of the spacecraft, but when the spacecraft's gone past, its gravity is trying to slow it down. And I think if you had a single point, that would be what would happen. You wouldn't gain any momentum from the encounter. The speed you gained on the approach to the black hole, assuming you're going fast enough not to get sucked in, would match the speed you'd lose on the way out. So the net effect would be zero. Because, as I understand it, it's to do with the planet's rotation and the direction that you approach it in relation to its equator that actually gives you the gravity assist. So it's to do with the structure of the planet itself that you can make this momentum change to give momentum to the planet. Sorry, to take momentum from the planet to assist your spacecraft in its journey. So I think the answer is probably no. Even, I'm not sure anybody would want to fly a spacecraft close to a black hole anyway, in case...
I'm sure there are people who would want to, but whether or not you'd be capable of it and come back to tell the story, that'd be a different thing, I imagine. But okay, so probably not is the answer to that particular question.
I will
Tom.
try and follow it up though, because it's a really interesting question, and it feeds into why gravity assist works at all.
Fascinating. All right. Thanks, Tom. Thanks, Richard, for your questions. We knocked over a couple of more of those text questions that have been racking up for the last 10 years. But we'll knock off some more. But if you do have a question for us, don't forget to visit our website and click on the AMA link. And you can send us a text question through the email interface, or you can use your recording device, whether it's through a tablet or a smartphone or a computer, and just tell us who you are, where you're from, and ask your question. Happy to run audio questions as well, which we've been doing a lot of lately, but catching up on the text questions too. And that's pretty well it. And thank you again, Fred, as always. It's great to see you, and happy trails, and we'll catch you again next week.
Sounds great, Andrew. Same to you. All the best. Speak soon.
Professor Fred Watson, Astronomer-at-Large, part of the team here on the Space Nuts podcast. Hello to Hugh in the studio, who works feverishly to put it all together and adds the nuts and bolts and finds the silly pictures that he puts on the graphics when we put them online. And from me, Andrew Dunkley, thanks again for joining us. We'll see you on the very next episode of the Space Nuts podcast. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.